A very good morning to my algebra lecturer, which is Dr. Shamila, and also my fellow friends. So, for today, I'm going to present my topic, which is application of vectors in roller coaster engineering. Alright, so when we think about the roller coasters, we usually think about the speed, the height, the sharp turns, and the excitement. The roller coasters are one of the most thrilling rides in amusement parks, and many people will enjoy them because of the fast motion and unexpected changes in direction. However, behind all the excitement, there is actually a lot of mathematics and engineering involved in the design process. The roller coasters cannot simply be built based on imagination alone. The engineers need to carefully calculate the track design, the movement of roller coaster, and also the safety of passengers. To do this, they use different mathematical concepts, and one of the most important concepts is factors. The factors are very useful because they allow engineers to describe the movement accurately. In roller coaster engineering, the coaster doesn't only move forward, it may move upward, downward, left, right, or even along a curved path. So, both magnitude and direction are really important. In this presentation, I will explain how the factors concepts such as the position factors, direction factors, resultant displacement factors, and also the factor components can be applied in modeling the movement of roller coaster. So first, let us begin with a simple introduction to factors. A factor is a mathematical quantity that has both magnitude and direction. This is what makes vectors different from ordinary numbers. For example, if we say 10 meters, it only tells us the distance but not the direction of the movement. In many real life situations, especially in motion and engineering, directions is just as important as distance. For instance, if a roller coaster moves 40 meters, we still don't know whether it's moved upwards, downwards, or sideways. Without direction, we don't get the full pictures. This is why the are important. They allow us to describe the movement more accurately by showing how far and which direction an object moves. In roller coaster engineering, this is very useful because the track is not straight. It includes slopes, turns, and drops. Engineers need a way to describe the motion in different directions at the same time. So the factors make it possible. That helps engineers analyze the coaster position, direction, and overall movement in space. Alright, so a factor quantity is a quantity that has two important elements, which is magnitude and direction. The magnitude refers to the size or the length of the factors. For example, if an object moves 5 meters, then the 5 meters is the magnitude. Direction tells us where the object is moving, such as north, east, or upward. When the magnitude and direction are combined, we will get a factor. The factors are usually written in a coordinate form. In two-dimensional space, a factor is written as bracket SY, where the S represent horizontal movement and Y represent the vertical movement. In three-dimensional space, we use bracket SYZ, where Z represent height. For example, the factor 4,3 means that moving 4 units in the x direction, then 3 units in the y direction. This can be shown as an arrow, where the length represents the magnitude and the direction shows the movement. The factors are widely used in many fields. In physics, they describe force and motion. In engineering, they help models structure and movement. So now let us focus on the key factors concepts that are useful in roller coaster modeling. There are three main factors concepts that I will highlight in this presentation. The first concept is position factors. The position factors describe the location of the roller coaster at a certain path relative to a fixed origin. And this helps the engineers know exactly where the coaster is on the track at any moment. The second concept is direction factors. The direction factors show the direction of movement from one point to another. In roller coaster design, this is useful because the track is made up of many connected sections, and each section has its own direction. The third concept is resultant displacement factors. When the coaster moves through multiple sections of track, these individual movements can be combined into one overall factor, and this resultant factor shows the total displacement from the starting point to the ending point. So together, these concepts help engineers describe the roller coaster's movement in a structured and mathematical way. Instead of only saying that the coaster goes up, down, or turns, the engineers can express this movement precisely using factor notation. So this allows them to study the coaster's path more carefully, predict how it will move, and make sure that the track design is safe and convenient for every passengers. And now I will explain the first concept, which is position factors. A position factor represents the location of an object relative to a fixed starting point, which is usually called the origin. The origin is often written as O bracket 00 in two-dimensional space or O 0 bracket 000 in three-dimensional space. If an object is located at a certain point, we can describe its position by drawing a factor from the origin to that point. This factor is called a position factor. In the context of roller coaster engineering, the position factors are useful because the roller coaster moves through many different positions along the track, and the engineers need to know that the exact location of the coaster at different times, especially when the track includes changes in height, slopes, and turns. For example, suppose the roller coaster is located at point P, which is bracket 4 to 3. Then the position factor from the origin to point P can be written as OP equals to bracket 4, 2, and 3. This tells us that the coaster is 4 units along the x-axis, then 2 units along the y-axis, and 3 units along the z-axis. In other words, the factor describes the exact location of the coaster in three-dimensional space. This is very important in engineering because the track of a roller coaster is not flat. It often rises and falls. So the z coordinate is especially useful for showing the height of the coaster. So by using position factors, the engineers can map out the roller coaster pathway clearly and easily and identify the location of each part of the track. The next important concept is direction factors. A direction factor shows the direction of movement from one point to another. In roller coaster engineering, this is useful for describing how the coaster moves along a particular section of the track. To find a direction factor, we subtract the coordinates of the starting point from the coordinates of the ending point. For example, suppose the roller coaster moves from point A which is bracket 1 2 1 to point B bracket 5 6 3. So to find the direction vector AB, we subtract the A from B. So the factor is AB equals to bracket for the x coordinate is 5 minus 1, and for the y coordinates x is 6 minus 2, and for the z coordinate is 3 minus 1. So finally we will get the answer bracket 4 4 2. So this means the coaster, the it moves 4 units in the x direction and 4 units in y direction, then 2 units in the z direction. So the direction factors are very useful because they help engineers understand how each section of the track is oriented in space. For instance, a direction factor can show whether the coaster is climbing upward, moving downward, or turning sideways. So this is important when connecting one segment of the track to another. The engineers want the transitions between the track sections to be smooth because sudden or sharp changes in direction can make the ride uncomfortable or unsafe. By analyzing the direction factors, the engineers can design the path of the roller coaster more effectively and make sure the tracks flows smoothly from one section to the next. Then, the third important concept is the resultant displacement factor. In many situations, an object doesn't move in only one single direction. Instead, it may move through several directions or sections. In this case, we can combine these movements using factor addition. And the final factor that represents the overall movement is called the resultant displacement factor. For example, imagine that a roller coaster first moves east and then move north. These are two separate motions, but together they produce one overall movement from the starting point to the final point. So instead of analyzing the two movements separately, we can combine them into one resultant factor. And this resultant factor gives us the net displacement of the coaster. This concept is especially useful in roller coaster engineering because the coaster often travels through multiple track segments. The engineers may want to know the total change in position after several movements, rather than looking at each movement individually. The resultant displacement factor helps the engineers simplify and summarize the motion of the roller coaster, and it gives a clear picture of where the coaster end up compared to where it started. This also helps when calculating the actual displacement distance and direction of the coaster from one point to another. Now, let us look at how factors are used to describe the motion direction of a roller coaster. When a roller coaster moves along a track, its motion is not just random. Every movement can actually be represented using something called a displacement factor. A displacement factor shows the change in position of the coaster from one point to another. It includes both how far the coaster moves and in which direction it moves. For instance, when the roller coaster is moving forward along a straight track, we can represent this motion using a factor pointing forward. This factor shows that the movement is in a straight direction with a certain magnitude, which is the distance traveled. Next, when the roller coaster is moving upward during a climb, such as when it is going up a hill, the direction of motion changes. In this case, the factors will point upward, showing that the coaster is gaining height. This is important because the roller coasters often have steep climbs that require careful design and calculation. Similarly, when the roller coaster is moving downward along a drop, the factor will point downward. This represents the coaster losing height as it goes down a slope or a step drop. These downward movements are usually the most exciting part of the ride, but they must also be designed safely. So, from these examples, we can see that different types of motion, whether it is forward, downward, or upward, can all be represented using factors. So by using displacement factors, the engineers can clearly describe and analyze how the roller coaster move along different parts of the track. This helps them design smoother tracks and ensure that the motion is safe and controlled. Then, another useful idea in factor mathematics is factor components. A factor can be broken down into smaller parts called components. In two dimensions, a factor is usually written as bracket Vx and Vy. Here, Vx represents the movement along the x-axis and the Vy represent movement along the y-axis. If in three dimensions, we can also include Vz, which represent movement along the z-axis. Breaking a factor into components makes the mathematical calculation much more easier. For example, when we want to add factors, subtract factors, or find the magnitude of a factor, it is usually easier to work with the component first. In roller coaster engineering, this method is useful because the coaster's motion can be analyzed separately in horizontal and vertical directions. The engineers can study how far the coaster moves forward, how far is rise or force, and how these movements combine together. By using the factor components, it gives the engineers a clearer understanding of the motion and helps makes calculation more systematic and accurately. Alright, here is the real life engineering application. And for first, factors help engineers predict the motion before construction. Before building the roller coaster, engineers use the mathematical models to simulate how it will move. With factors that can predict the path, speed, and direction of coaster, allowing them to test and improve the design earlier. Second, factors are used to represent the direction of the track. Each section of the track has a specific direction, whether it is straight, curved, going upward, or downward. Factors help engineers describe this direction clearly and visualize the full track layout. Next, factors help engineers analyze changes in the direction along the ride. A roller coaster constantly changes direction through turns and slopes. By using factors, engineers can ensure these changes are smooth, which involves both safety and passengers' comfort. Finally, factors are used to determine the displacement between 2 points. This shows the overall movement from one point to another and helps engineers plan the track move efficiently. Then, now I will move on to the first problem scenario. This scenario focused on the horizontal movement of a roller coaster along two sections of track. Imagine that the coaster starts from one point and first move 40 meters east. After that, it changed the direction and moved 30 meters north. These two movements can be represented using vectors. The reason we use vectors is because each movement has both a magnitude, which is the distance traveled, and a direction, which is east or north. This scenario is a simple example, but it clearly shows how the factors can be used to analyze the movement of an object. From this situation, we will be able to find the resultant displacement, the total displacement distance, and the final direction of movement. Alright, for this scenario, the first movement is represented by factor A, which is bracket 40, 0. This means the roller coaster moves 40 meters along the x-axis, which represents east, and 0 meters along the y-axis. And the second movement is represented by factor B, which is bracket 0, 30. This means the roller coaster, it will move 0 meters along the x-axis and 30 meters along the y-axis, which represents north. So from these two factors, we need to determine three things. First, we need to find the resultant displacement factor. And second, we need to find the magnitude of the displacement, which tell us the straight line distance from the starting point to the ending point. And the third, we need to determine the direction of the displacement, which tell us the final direction in which the roller coaster has moved overall. And this problem demonstrates how the factor addition can be used to combine separate movements into one complete result. Now, let us move to the second scenario. Unlike the first example, which only involved horizontal movement in two dimensions, this scenario involves motion in three-dimensional space. And this is more realistic in roller coaster engineering because the roller coaster are not limited to flat motion. They often move upward and downward as well, especially when the track includes slopes, drops, or rest section. In this example, the roller coaster moves between 2 points in space. By using vectors, we can describe the movement between these points and also calculate the distance traveled in straight line. This helps show how vectors concept can be applied to more advanced and realistic engineering situation. In this scenario, the starting point of the roller coaster is A, which is bracket 2, 1, 3. And the ending point is B, which is bracket 8, 5, 7. This coordinate shows that the coaster changes its position in all three directions, which is S, Y, and Z. From this information, we need to determine two things. At first, we need to find the position factors from A to B, which describes the movement from the starting point to the ending point. And second, we need to find the distance between 2 points, which is the magnitude of that factor. This problem shows how the factors can be used to model the movement through the three-dimensional space, which is very important in roller coaster design. So now, let us solve the first scenario. To find the resultant displacement factor, we need to add the two given factors, which is factor A is bracket 40, 0, and factor B is bracket 0, 30. So we just, when we add the corresponding component, we will get for bracket 40 and 30. So the resultant displacement factor is bracket 40, 30. This means that overall the roller coaster has moved 40 meters east and 30 meters north from this starting point. Next, we find the magnitude of this resultant vector. The magnitude tells us the straight line displacement from the start to the finish. After calculation, the magnitude is 50 meters. This means that although the coaster moved in two separate sections, its total displacement from the starting point is 50 meters in a straight line. This example is similar to forming a right triangle, where the eastward movement and the northward movement are two sides, and the resultant displacement is the hypotenuse. Then finally, we determine the direction of the displacement. To find the direction, we use the tangent ratio. We take the vertical movement divided by horizontal movement, which is 30 divided by 40. So we calculate the antitangent 30 over 40. After calculation, we can get an angle approximately 36.9 degrees. This means the roller coaster moved at an angle of 36.9 degrees north of east from this starting point. So overall, the coaster doesn't just move east or north, but in a diagonal direction between two. Then, let us solve the second scenario. To find the positions vector from A to B, we subtract the coordinates of point A from point B. The point A is bracket 2, 1, 3, and the point B is bracket at 5, 7. So the factor from A to B is B minus A, which is for the x-axis 8 minus 2, and for the y-axis 5 minus 1, and for the z-axis 7 minus 3. This gives the answer 6, 4, 4. So the position factor from A to B is bracket 6, 4, 4. This means the roller coaster moves 6 units in the x direction, 4 units in the y direction, and 4 units in the z direction. Next, to find the distance between 2 points, we calculate the magnitude of these factors. After calculation, the distance is approximately equals to 8.25 units. And this is the straight line distance between the starting point and the ending point. This example is important because it shows how the factors can model the movement in three-dimensional space. In real roller coaster tracks, the movement is rarely limited to only left and right. The height changes are also involved. So, the three-dimensional factor analysis is very useful. Then now, let us look at the role of factors in decision making and optimization in roller coaster engineering. When engineers design a roller coaster, they must work within several deep important constraints, not just focus on excitement. First, there are G-force limits. If the coaster moves too fast or changes direction suddenly, it can be dangerous. Factors help engineers analyze motion and control acceleration to keep the ride safe. Second, there is a material strength. The track must withstand strong forces, especially during turns and drops. Factors help calculate these forces to ensure the structure is strong enough. Third, there are budget limitations. Engineers must design efficiently without overspending. Factors analysis helps optimize the design while reducing costs. Finally, there are space restrictions. Roller coaster must fit within a limited area. Factors help plan a track layout effectively. And this is the example that shows that mathematics is not just abstract theory but something that is used in real world application. The roller coaster engineering mathematics is very important to ensure that the ride is safe, functional, and enjoyable. Without factors, many aspects of design cannot be properly analyzed. First, without factors, directional force cannot be calculated. When a roller coaster moves, factors act in the different directions such as forward, upward, downward. Factors help engineers present both magnitude and direction, allowing them to understand how this force affect the motion. Second, without factors, loop motion cannot be analyzed. Loop involve continuous changes in direction. Factors helps engineers study this motion and ensure the coaster stay safely on track. Third, without factors, safety limits cannot be verified. Engineers use factors to calculate acceleration and g-force to make sure passengers are safely during the ride. Overall, this shows that mathematics has a direct impact on a real-life engineering. So in conclusion, the factors play a very important role in modeling motion and position in real-life situations, especially in engineering. In roller coaster, engineering factors help describe where the roller coaster is, how it's moved, and the overall displacement from one point to another. Throughout this presentation, we have seen several important factors concepts including position factors, direction factors, resultant displacement factors, and factors component. This component allowed the engineers to represent the movement of the roller coaster clearly and mathematically. By applying factor mathematics, engineer can design tracks more accurately, analyze the path of motion, improve safely, and create smoother and more efficient rides. So overall, vectors are important parts of the roller coaster engineering because they help transform mathematical theory into real design application. So that's all from me. Thank you for listening to my presentation.